Yes, sir. We will start, sir. 1 second.
Right. Yeah.
Ma'am, Inila ma'am.
Okay, sir.
Yeah. KP sir. Please start, sir.
A very good morning to everyone. The Department of ECE heartily welcomes the dignitaries, the guest of honor, and the participants to the AICT sponsored 1 week online STTP on mixed signal design from 26th to 31st October 2020. Let us start our proceedings with the traditional Lightening the Lamp along with a prayer song. I invite Miss Chinmayi to offer the prayer song. Chinmayi, please.
मुदाकरात्तमोदकम् तदा विमुक्तिसाधकं कलाधरावतंसकं विलासि लोकरक्षकम् अनायकैकनायकमासिते भदैत्यकं नतासुभासुनाशकं नमामि तं विनायकम् जय गणेश जय गणेश जय गणेश पाहि मां जय गणेश जय गणेश जय गणेश रक्ष मां न तेतरातिभीकरं नवोदितार्क भास्वरं न मत्सुरारिनिर्जरं न ताधिकापदुर्धरम् सुरेश्वरं निधीश्वरं गजेश्वरं गणेश्वरं महेश्वरं तमाश्रये परात्परं निरन्तरं जय गणेश जय गणेश जय गणेश पाहि मां जय गणेश जय गणेश जय गणेश रक्ष मां जय गणेश रक्ष मां जय गणेश रक्ष माम्
Ma'am, unmute yourself, ma'am. Inila madam.
Okay, sir. Thank you, Chinmayi. VVIT was established in 2007 by Sri Vasireddy Vidyasagar Garu under the Social Educational Trust. VVIT has self-contained infrastructure amidst the lush green paddy and maize fields of Nambur. VVIT is accredited with NBA and NAC A grade and is permanently affiliated to JNTU Kakinada. The institute has been conferred with autonomous status in the year 2019. VVIT offers 10 undergraduate programs and 5 postgraduate programs with a total intake of 1341 students every year. The main objective of the STTP entitled Mixed Signal Design is to clearly describe the importance of dynamic changes in the VLSI design technology, fabrication, test, diagnosis, and verification of complex design chips, and also to discuss the recent trends. We have here a wonderful opportunity to learn experts of this field, not only theoretically, but also the practical aspects through this 1 week STTP. I invite our head of the department, Dr. M.Y. Banumurthy Garu, to give a brief report on this STTP. Sir, please.
Thank you, Vanilla madam. respected chief guest of today's inaugural program, Dr. Pushpa Garu from NIT Patna, principal of our institution, Dr. Y. Mallikarjuna Reddy Garu, Dean of Academics, Dr. Kumar Swami Garu, Dean of Studies and Professor of ECE, Dr. K. Giri Garu, all the faculty members of VVIT and the participants from other institutions and organizations. Good morning to one and all. I welcome you all on behalf of the Department of ECE to this 1 week STTP on the mixed signal design. At the outset, I would like to thank the AICTE for granting us or sanctioning the STTP. And in view of the STTP being online, we are conducting this STTP on in 3 phases. So phase 1 is on mixed signal design, and phase 2 and 3 will have a blend of wireless communications, the machine learning, and also VLSI. So as you might have already seen the brochure where we have a good blend of academicians as well as the experts from industry, and the hands-on sessions will be through virtual labs which will be provided by Apply Volt. So we thank all the resource persons for accepting our invitation and sparing their time in sharing their knowledge. So I do hope all the participants will get benefit from all these sessions, and I really wish all the participants to attend all the sessions regularly without fail, and expand your knowledge base, and do earn the participation certificate from us. Finally, I would like to thank our management for their constant support and encouragement, and for giving us these opportunities to conduct various STTPs and FDPs for the faculty of our institution, and also to other institution faculty members and research scholars as well. Thank you so much.
Thank you, sir, for briefing the session. I now request our Dean of Academics, Dr. N. Kumaraswamy Garu, to address the participants. Sir, please.
Good morning to everybody. Is it audible to you?
Yes, sir.
Yes. Good morning to everyone. Myself, Dr. N. Kumaraswamy, Dean of Academics. Respected dignitaries, today's guest of honor, Dr. Pushpa Garu, our beloved principal, Mallikarjuna Reddy Garu, Dean of Studies, Giri Garu, HOD of ECE, Bhanumurthy Garu, my learned colleagues, my dear participants. It is a matter of pride and immense pleasure to welcome all for this STTP program on mixed design of the signals. Pandemic COVID 2019 create opportunity everyone to go innovative way of for learning and teaching. In normal situation, every learner cannot get opportunity to interact with eminent personalities and experts in various fields of engineering all over the world. To enhance your learning process and applications aspects on emerging technologies and public domain technologies, that means Industry 4 technologies are essential. I advise all the participants to conduct similar type of training programs through online, and your colleagues, and give a project works on these topics for final year students, and also give projects for third year and second year students. After completion of this course, you will definitely gain more knowledge with less time and with less expenses. It will be all fruitful, unforgettable experience in coming few days from this training program and from the experienced expert lectures. I appreciate motivation, encouragement from AICTE, our management, beloved chairman, Sri Vidyasagar Garu, Secretary Badri Prasad Garu, Joint Secretary Sri Krishna Garu, our beloved principal Mallikarjun Reddy Garu, and efforts of Dean of Studies Giri Garu and Dr. Bhanumurthy Garu, coordinator and HOD ECE for this program. Dr. Bhanumurthy Garu is highly energetic, dynamic and committed person. Definitely, he will justify his role as a coordinator of this training program. Thank you for all. Once again, I welcome all the participants. Thank you for giving this opportunity for organizers. Thank you one and all. All the best.
Thank you, sir. Thank you for your encouraging words. Now let me invite Dr. K. Giribabu Garu, convener and Dean of Studies, to speak a few words on this occasion. Sir, please. Hello, sir.
Okay. Respected Principal Dr. Y. Mallikarjun Reddy Garu, Dean of Academics Kumaraswamy Garu, HOD Bhanumurthy Garu, today's keynote speaker Professor Pushpa Garu, my dear participants, a very good morning to one and all, and my warm welcome to all who are from various institutions and R&D organizations. I would like to congratulate the Department of ECE for taking up this mixed signal design broad theme in a three-layered manner for the STTP series to cater the fundamentals of VLSI design, the current research aspects of mixed signal design along with its applications, and then to a pinnacle of the futuristic trends, latest developments in this arena. This series will definitely support to upgrade the abilities of engineering educators and thereby the skills of students, researchers, and aspiring developers in the electronics and communication engineering sector. I thank and honor the acceptance, readiness, and virtual presence of the distinguished keynote speakers, resource persons who are going to share their invaluable knowledge. I thank our Principal Y. Mallikarjun Reddy Garu and Chairman Sri Vasireddy Vidyasagar Garu, who support us always to take up any challenging step forward into the realization of our VVIT's vision. I am proud to say that VVIT always stands ahead in supporting every activity that will motivate true engineering educators and researchers. I once again convey my best wishes to all the participants of this STTP, first phase of STTP, who are all set on this virtual platform, ready to imbibe every key point of this STTP series, starting from this mixed signal design. I wish this STTP will achieve its objectives in a fruitful manner. Thank you one and all. Thank you.
Vinila madam, unmute yourself, madam. Vinila ma'am.
minute, sir. Thank you, sir. Thank you for guiding us. I request our esteemed principal, Dr. Y. Mallikarjun Reddy Garu, to address the participants. Sir, please.
Okay, thank you, madam.
Thank you, sir.
Today's function, respected chief guest and keynote speaker, Dr. Pushpa Giri Garu from NIT Patna, and our beloved chairman, Dr. Mosfet Vidyasar Garu, management members, Dean of Academics, Dr. Kumar Swami Garu, and the Dean of Studies, Dr. K. Giribabu Garu, and Head of Department, Dr. Vanmurthy Garu, and my dear staff members, and the participants from different engineering colleges. Welcome to all for this 1 week STTP program on mixed signal design. So at the outset, once again, I welcome all the participants to this 6 days program, and I wish all them to participate in all the days without any absentees, such that you can learn a lot of things from the resource persons. As you know that the resource persons are taken from the experts from NITs and IITs, so they will give a lot of inputs to the participants, such that the program can make a grand success for that. So as you know that the challenging of mixed signal design, as you know that the mixed signal design having a lot of impact on the technology nowadays. So for the development of computer science and information technology or software, whatever may be that, so the basic the design starts from the electronic side. So as you know that a mixed signal design is having a designing the digital and analog on a single chip, right? And also a programming such that we have to communicate the signals, analog as well as the digital, right, through one integrated circuit. So for which we require a lot of knowledge on the CMOS technology, networking, communications, and protocols of different technologies. So nowadays we see that there is a 5G technology that is upcoming. So the development of 5G technology is based on the mixed signal design only that. So by learning the subject on this topic, mixed signal design, the students can learn a lot of things on the how to programming the VLSI design, such that you can make the high-speed communication. Because you see that there is a nanotechnology is upcoming. So as you know, the frequency is increasing, the voltage levels are dropping, and we had to face a lot of the complexity in the signal design, right? So which we have A to D converters, D to A converters with high speed technology, and also in the processors, smartphones, smart TVs. So whatever you have taken in the smart applications, the mixed signal design is involving, and it is take a lot of challenges nowadays we had to face with the signal frequency. Suppose the frequency is more than 1 gigahertz, then there is a lot of complexity is increasing. Then we have to look after the thermal conditions and the signal levels and the clarity of the signal, and also with high speed technology. So all these things are involved in the designing of mixed signals, right? So therefore, in this 6-day program, the participants will learn the maximum the inputs of all the technology, and it alludes to 5G and nanotechnologies that we are going to implement in future, such that we can have a lot of applications in different areas, in different areas that you could like. So irrespective of the electronics or communication engineering, right? It also involves, right, in robotics, right, and 3D technology, 3D design technology, and all these things. So therefore, it is very, very important, and there are a lot of challenges that will be learned in this due course, right? So once again, I thank all the participants who are attending this program, and also the resource persons, right? So giving the inputs to the participants and the staff of EC department, and especially Dr. Bhanumurthy Garu for arranging the signal, and also the AICTE given the sponsorship for this programming. So once again, I thank you all, and thank you very much for this. So thank you, sir.
Thank you, sir, for the valuable insights you have given us. Now, our esteemed guest, Dr. Pushpa Giri Garu, is from NIT Patna. I request Mr. S. Krishna Prasad Garu to apprise the achievements of our honorable guest. Sir, please.
Thank you, madam. Respected dignitaries, colleagues and dear participants, a very good morning to one and all. As we all are aware of, over the past couple of years, mixed signal design has been emerged as the most technically tough and interesting segments of the semiconductor industry, as well as academic research. As our principals are already addressed, for many emerging domains such as Internet of Things and artificial intelligence, one continuous requirement is to ensure that the analog real world where we are living in to connect seamlessly to the digital computing world. So mixed signal design plays a vital role in achieving this. We are fortunate to have experts from both industry and academia addressing the sessions in this STTP to share their knowledge and expertise. Now I take this privilege to introduce our guest of honor and also a research person for today's session, Dr. Pushpa Giri Garu. Dr. Pushpa Giri Garu has obtained her BTech degree from University Institute of Technology, RGPV, Bhopal in the year 2010. She did her master's from MNIT Allahabad in 2013 and her PhD from MNIT Allahabad in 2016. She is currently working as assistant professor in the Department of ECE, NIT Patna. She has many high-impact publications in reputed journals like IEEE Sensors. Her research interests include microelectronics and VLSI design, fabrication and characterization of thin films and nanostructures, nano-electronics, and photonics. We are very fortunate to have you here, ma'am. I request Pushpa Giri, ma'am, to address the participants. Ma'am, please.
Thank you so much, sir, for giving me this opportunity, and thank you so much for praising me this much. So first of all, I would like to say good morning to all. And I'm very much thankful to Dr. Basu and the Institute VVIT for providing me an opportunity to share my views in related domain on such a great platform and in front of the audience like you. So I hope that I'll deliver the stuff that will be beneficial to researchers and which they are going to start their career like UG, PG or PhD scholars and faculty as well. So I'm Dr. Pushpa Giri here. Today I have some collection about the nanoscale fabrication and related things. So with this only, I'll start my session. So shall I start, sir?
Thank you, ma'am. Just a while.
Okay,
we'll
sure.
close the inaugural session and then we can start the keynote session, ma'am.
Okay, okay. Thank you.
Thank you, ma'am. We are grateful to you for sharing your. I invite Mr. K. Vasubabu Garu, co-coordinator, to the STTP to deliver the vote of thanks. Sir, please.
Thank you, madam. Good morning to all. First of all, I thank to our head of the institute, Dr. Y. Mallikarjun Reddy Garu, principal, and Dr. N. Kumar Swamy Garu, Dean of Academics, and our beloved HOD sir, Dr. M. Y. Bhanumurthy sir, and convener of the program, Dr. K. Giri Garu, Dean of Studies. I thank to all to attend the inaugural program of AICTE sponsored 1 week online STTP program of phase 1 on mixed signal design, conducting from 26th October to 31st October 2020. This entire STTP, we select the resource person from IITs, NITs, and reputed universities from other one, and also taken from the industries also. What is the current research going on VLSI? How they can design the front end and back end tools for designing of nanotechnology present cases, and the development of how they are going in industries, developing of their chips, all are we can arranging down. And also we arranging one more program on virtual lab, and with the help of we apply volt, we take a permission from virtual lab, one complete section 2 hours on Saturday morning we can conducting, and this is taken from completely the information what they are running in the present technology, what is the softwares they required, how who are doing the research or industry needed, what is the platforms required for to manufacturing of that cheap present nanoparticles, how we can design the frequencies is greater than 20 gigahertz. Just at that particular case, how they are using the chips for the industry, they can providing all are they can take one of the tool and the conducting the one lab session by apply volt. This is conducting on Saturday. And then I thank to today's resource person, Dr. Pushpa Madam, NIT Patna. Madam, asking for this AICTE got the permission, we can ask for delivering your lecture, present technology, what is going on the mixed signal design. And I thank to Dr. Pushpa Madam Garu to accepting the our invitation and delivering of sessions in the concept of Madam delivering for how the industry is needed for the resource for researchers in the domain of mixed signal design. And then the topic related to nano-electronics for the next generation for mixed signal design, how we are combining for digital and analog signals for generation of VLSI industry needed. The resource persons are academic persons are the students who are learning their knowledge and the subject, how we can utilizing of that one to our industry needed, she can explain. And finally, I thank to all our department faculty members who are arranging all the programs, conducting for the resource persons, or how can we can utilize all those things are using with the help of. I thank to all our department HOD sir and then our all colleagues, and I thank to give this opportunity. Thank you, madam.
Thank you, sir. I now request Dr. Pushpa Garu to deliver the keynote session. Ma'am, you can continue the session. This is the first session.
Okay, ma'am. Thank you so much.
Thank you, ma'am.
My screen is visible?
Yes, ma'am.
Okay, okay. Once again, good morning to one and all. So I am Dr. Pushpa Giri. So I'm going to discuss about the things which actually it is going in the recent times, like nano-electronics for the next generation mixed signal design. As as told by everyone, like principal sir, HOD sir, and everyone, like how this mixed signal design is very much important in these era. But these mixed signal design actually it has been originated from the nano-electronics itself. So how these two, these nano-electronics as well as this mixed signal design and mixed signal ICs, how these things, these are going to be merged all together. Okay, so I am going to discuss all these things only in today's session. Okay, am I audible, ma'am?
You are audible, ma'am. You can continue.
And slide is also visible?
Yes, ma'am. Yes, ma'am.
Okay, thank you. So first of all, I would like to introduce, or I would like to describe little bit things mixed signal design. Then I'll go further for the nano-electronics, and then we will see what is the future scope of our these two things, how these two things can be collaborated, and we can get the new things in the future scope. Okay. So first of all, I would like to tell about the mixed about the mixed signal design. So mixed signal design or mixed signal integrated circuit, as we are talking about the VLSI, so everything is integrated circuit only. If I'm talking about the designing part, so designing is nothing but integrated circuit, and we all know that integrated circuit is nothing but we are going to accommodate, or we are actually going to fabricate our active elements and passive elements into a single substrate, right? So that is called the integrated circuits. Or if I'm talking about the VLSI design, so in the designing part, I'm actually going to fabricate the integrated circuit. So we are going to talk about the mixed signal ICs or mixed signal design. So mixed signal integrated circuit is nothing but it is also any integrated circuit only, which is having both the circuits, or you can say it is a combination of both the circuit, that is analog circuit as well as digital circuit on a single substrate, or we can say on a single semiconductor die. Okay, so generally in the ICs, we are actually fabricating, we are generally fabricating, earlier days we were fabricating the analog circuit separately and digital circuit separately. Okay, but as the complexity of these days, our demands are getting too much high, so in order to fulfill those criteria, actually we have to fabricate these two things all together. Okay, so we can say like analog circuit as well as digital circuit, we are actually going to fabricate on a single chip. So that's why this is called the mixed signal integrated circuit. Okay, so I can give you one very real life application. We can give, like, mixed signal designs are everywhere these days. So generally we are using the smartphones. So smartphone is nothing but it is also an example of our it is also an example of the smart mobile phones, the example of mixed signal design. Okay, so mixed signal ICs are also process both the analog and digital signals together. For example, analog to digital converter is there. So analog to digital converter, or ADC, is a mixed signal circuit. So mixed signal circuit are systems, typically these are the cost-effective solution for building any modern consumer electronic application. So because of these many reasons and because of these many applications, we are actually using the we are actually going to use this mixed signal design, or we can say, in another words, if I'll say like an analog mixed signal, it can be a combination of in another words, if I'll say, like, it is a combination of analog circuits, digital circuits, intrinsic mixed signal circuits, and embedded software. Okay, so just to before what I was talking about the integrated circuits. So integrated circuits, already I defined what was that, like individually we were connecting the digital circuit and analog circuit. So digital circuit, if I'm talking about, so it can be like microprocessor, it can be, for example, or this circuit, if you can see, this is a PAL circuit. Okay, so these are the digital circuit. And if I'm talking about the analog circuit, so it can be like operational circuit, which you can see in the slide. Okay, and our mixed signal ICs are obviously, it is a combination of both the circuits. So like this category of the chip, it has grown dramatically with the increased use of like 4G cell, and just now the principals are told about the 5G cell phone. So in the 5G cell and the 4G, actually these mixed signal design, these both the things, it are actually being used widely. And if we are going for the other portable technologies also, so this particular technology, actually it is being used. And the mixed signal IC are often used to convert like analog signal to digital signal, so that digital devices can process them. For example, we can say like in the FM tuner also we can use, like mixed signal ICs are essential component for FM tuner in in digital products, such as you can say like media players which have a digital amplifier. So any of these things, like whatever, wherever I mean this analog signal and this what you can say the digital signal, both are required. So each and every field we need these two things. Earlier, single things were being done, so separately these two things were done. But nowadays we are actually combining, so that we can get more and more application in variety of areas. So any analog signal such as FM radio transmission, or a light wave, or a sound, it can be digitized using a very basic analog to digital converter. And the smallest and most energy efficient of these would be in the form of mixed signal ICs only, right? Sorry. Actually, I'm having little cold and cough, so please excuse me. So, as we are having many options in a different area, in a different field, so not easy things, like if I'm going to fabricate, if I'm going to design this analog part as well as digital part, because individually if I'm going to do it, it can be a short span of time, as well as with the ease also we can fabricate. But when it comes to do all, then the fabrication and designing, manufacturing, it's little difficult. for example, efficient IC, it's digital and analog component, and it is sharing a common power supply. That is the most important thing whenever we are designing circuit, whether discrete circuit or whether it is integrated circuit or whether it is a mixed signal integrated circuit. So everywhere power supply is very much important. So generally, if I am fabricating these things into a single chip, so what is happening? We need to give a same power supply to both the things, like analog circuit as well as digital circuit. That means these two components, they need to share a common power supply. However, analog and digital components have a very different characteristics. Make this design. So the important things we should have to keep in our. So so many examples are also there, like already we have discussed, like cell phone is there for mixed signal ICs, DVD, system on chip, and like what you can say, if I'm going for the example of mixed signal ICs, include the data converter using delta sigma modulation we are having in the communication. If I'll go like analog to digital converter, digital to analog converter, it is there using error detection and correction, and digital radio chips are there. So everywhere from communication to digital electronics to nano-electronics, everywhere this mixed signal design part or mixed signal ICs we are using. So digitally controlled sound chips are also mixed signal circuits, and with the advent of the cellular technology and network technology, this category now includes cellular telephone, or you can say software radio, LAN, WAN router, integrated circuit. So everywhere we are going to use this mixed signal IC. So because of the use of the both digital and both digital signal processing and analog circuitry, mixed signal ICs are usually designed for a very specific purpose, and their design requires a level of expertise and definitely the careful
Excuse me, ma'am. Please excuse me once. If you
Yes,
are
yes.
if you are having any trouble, means you can take 5 minutes time, ma'am. So no problem. You can take. You can.
Just for a while I'll take my cough syrup and then I'll be
Yes,
back.
yes, ma'am. Yes, ma'am. Yes, you can take. You can take a
Please
break.
excuse me for this.
Sure, ma'am. Sure, ma'am. Sure, ma'am. Thank you. Participants, please wait for 10 minutes. Ma'am will have a break and she will be back.
Not 10 minutes also, just in 1-2 minutes I'll be back. No
Okay,
issue.
okay, okay.
Unmute, sir.
Yes, I'm back. So, what I was discussing was like because of the use of both the digital signal processing and both the signal processing and analog circuitry, the mixed signal ICs are for a high level of use of computer to having so many tools we are actually using this purpose, like we are having the cadence, we are having the mental graphics, we are having the synopsis, we are having the TCAD, virtual TCAD, like in TCAD also we are having the Silvaco, Centaurus, and all those things which actually they are going to use for the device level, circuit level, and layout level, front end, back end. So many, I mean, tools we are actually having, like computer aided design tools we are having. So whenever we are actually discussing about the mixed signal ICs, so we need to be very much careful because it is having a wide variety of applications, and we have to specific, I mean, definitely we are having a specific purpose and design requirements. So we need to be very careful. Automated testing also of the finished chip can also be so these are the things like we are, and so with this we are having so many things. So but some limitations also we are having some challenges, like altogether we cannot use a digital IC, analog IC altogether. We cannot, like PN junction diode is there, so we cannot I mean sandwich these two things and we can get the output, right? Because it is having a very big application. So definitely in the fabrication, during the fabrication time and during the manufacturing time, we are actually, it is a little bit difficult to achieve all those things, right? Because application is wide. So definitely at the manufacturing level or fabrication level, we need to give very much importance, and in terms of all the things, like very small things also we need to be considered. So like challenges, first of all we'll discuss about the challenges also. So some actually not very much, but I mean some of the challenges I have I found, and I would like to discuss with you is like CMOS technology. Actually in the CMOS technology is usually the optimal for digital performance and scaling, while bipolar transistors are and BJT are usually optimal for analog performance, right? Generally in the CMOS, whenever we are talking about the digital ICs, we are going for the CMOS, and whenever we are dealing with the analog performance, so we are going for the BJTs. So yet until the last decade, it has been difficult to either combine these cost effectively or to design both the analog and digital in a single technology without serious performance compromises, right? So the advent of the technologies like high performance CMOS, BiCMOS, CMOS toy, silicon germanium. They have removed many of the compromises that previously had to be made. Like whenever we are, whenever we can see, like I mean, from the VLSI point of view, when we are going to use the Mosfet, whenever we need a very small area to fabricate the things, or from the fabrication point of view, Mosfet is a very good candidate because it is having a planar structure, so it can be easily we can fabricate into the chip area, right? And when BJT we are using, generally wherever we need a high switching speed, right? So these are the two things separately we were using. But what will happen when we need a small area as well as we need a high switching speed? So what we need to do, we need to keep these both the things like CMOS as well as the BJT, so that BiCMOS came into the picture. So that by using the BiCMOS, what we did, we could able to achieve the very high switching speed, as well as we could able to fabricate the device in a single chip area with a minimum size or minimum area. Okay. So these were the challenges, and these challenges can be removed also. Okay. So these are the one of the very topmost challenge, but it can be eliminated. By using these two things. But we have to keep so many things into our mind while we are going to fabricate. Next one is the testing. So testing functional operation of a mixed signal IC remain complex. Although all the testing things, like whenever we are going to test any chip, so it is very tough to test, because we are having so many complex testing schemes. We are having like BIST is there and scan test is there, and so many testing schemes are there by which we can test our circuits. Okay. So and that too, when we are testing the individual, like digital circuit dependent testing and analog circuit we are testing. So definitely at that time also the testing function or testing operation, it is difficult to achieve. So think about those times when we are actually combining both the circuits together and then we are testing, right? So it is getting little more complex. It will be little more expensive, or often one-off implementation task, you can say, right? So this is also, I mean, this is the second challenges. This is the second challenge we are actually facing when using the mixed signal. Next one is like analog circuit. Next one is systematic design methodologies. Actually, it is comparable to digital design methods, are far more primitive in the analog and mixed signal arena. So analog circuit design cannot generally be automated to nearly the extent that digital circuit design can. But combining the two technology multiplies these complications. But the thing is, actually, systematic design approach and methodologies, these are the actually we need to actually go through in this area. Okay, like design methodologies and the systematic approach we need to follow. Okay, next one is the fast changing digital signal send noise to a sensitive analog inputs. Because what is happening, both the signals, see, we have to understand, like both the signals are different, like digital signals are different from the analog inputs. Okay, so a digital signal, it is fast changing, and analog inputs are a little bit different. So what is happening? Because of the mismatching of the signal, or because of the mismatching of the input, we are actually facing a lot of noise or some error we can get through. So one part for this noise is a substrate coupling. Okay, a variety of techniques are used to attempt to block or cancel this noise coupling, such as fully differential amplifier, or you can say the P plus guard rings are also available, like latch-up conditions are also there in the bi-CMOS circuit. I mean, I hope you would have heard about those. So some guard rings are also available. Differential topologies also we can use, or on-chip decoupling also we can use, or triple well isolation. So these are some techniques are available in our field by which we can block or we can cancel the noise of this mismatching of our input supplies. So I hope I will deliver to things like mixed signal and what is the mixed signal ICs, what are the advantages of mixed signal design, and what are the applications of mixed signal design, and what are the challenges also. Because challenges is nothing but challenges is actually the research gap. Like already these things happen, but these are the challenges on which I can work. Okay, like these are the things. If I'll apply, for example, if I want to reduce my noise, so what I can do? So I can apply like fully differential amplifier. I can apply the guard rings. I can apply the differential topologies, on-chip decoupling, and substrate coupling also I can apply. So these are the things by which noise can be removed, right? And before that we have discussed like analog circuit design cannot generally be automated. So we have to, systematic design methodologies we need to do so. And we had at the last stage when our chip is ready, at that time testing is little bit complex. So we have to find out the best testing scheme by which it can be tested smoothly and with the less error. Okay, and the first one was like how it can, both the things it can be combined so that we can optimize the device. So these are the challenges, or you can say these are the research gap by which we can apply in our research so that we can actually achieve whatever right now we are, so we can achieve little more, right? So with this, actually mixed signal integrated circuit and all the things we have discussed till now. So integrated circuit, that means nothing but we are going to fabricate the thing. So fabrication is very, very, very important. Without fabrication we cannot get the chips. Okay. So I would like to discuss little more about the fabrication techniques. What are the techniques available in the market, and which technique is best for which technique is best for fabrication of any device, and how this device can be fabricated. What are the research gap? What are the future scope we can do in this particular field? How this it is going. Seeing integrated circuits. So definitely we are working on the nanoscale, right? Intel, it is working on the 3 nanometer, 5 nanometer range. So definitely we are in a nanoscale range only. Like our phone is there, laptop is there, everything. It is based on the nano field, right? Nanoscale things. We are going these days, antennas, they are making a very nano absorber, reflector, and all those things, right? So everything, like all our all reactive it is going into the nanoscale. So already we are VLSI people, like we are the researcher in the field of the VLSI. So how we can leave this thing. Okay. So as we are going for the VLSI, that is very large scale integration or very large integrated circuit. So in this field, the basic building block you can see components and the passive components. These are the very small things. Active component like Mosfet is there, BJT is there, diode is there. Okay, the so do you know the history of the Mosfet, how it came into the picture? Like, it is a very fascinating story, like how, how this Mosfet came into the picture and who invented this Mosfet. So, like, as you can see the slide, like Mosfet, it was by Kala, and there were these two people. Actually, these two people, they fabricated scale Mosfet in the year of 1915. So they developed both the PMOS and NMOS processes for the Mosfet semiconductor device fabrication. So it was very fascinating story related to this, how these two people actually in the 1950s, like 1959 itself, they did. After that, in the 1960s, this Atala and Kang, actually they fabricated with the oxide thickness of 100 nanometer. Earlier, they have given the basic structure and they have they have in the nanoscale range, or you can say the nanolayer transistors. So first MOSFET, with the gate oxide like thickness with a gate length of 20 microns. Okay, generally whenever we are talking about the device, or whenever we are talking about the technology, generally we are in the 1962, you can say. So all these things, they were they were working in the Bell Lab, USA. Okay, so in the 1962, like at a layer-based metal semiconductor junction, that is MS junction transistor. The device has a metallic layer, with the metal forming the base and the semiconductors forming the emitter and the collector. So with its low resistance and the short transit times in the thin metallic nanolayer base, the device was capable of a high operation frequency compared to this bipolar transistors. So these were the very, what you can say, very interesting and fascinating stories, like related to this MOSFET and how it, how they shifted to this after that, their pioneering work involved depositing the metal layer on top of the single crystal semiconductor substrate, with emitter being a crystalline semiconductor piece with a top or blunt corner pressed against the metallic layer. After that, they have deposited the gold thin film with a thickness of 10 nanometer on N-type germanium, while the point contact was the N-type silicon. So in the, we can think, in the 1960s itself, these two people, they have fabricated in the nanometer. At that time, nobody was even they cannot even imagine also that nanometer range what it could be, because at that time only, like if you will think like the first computer, when the first computer was made, so what was the size of that particular computer? It was a huge, like a room size computer only, right? So this Atala and this Kong, they have actually in the 1959 and 1960s itself, they have given the nanometer scale range device. So it was total beyond imagination. After that, these two people, they worked into what they have extended their work, and they started their work on hot carrier devices, which used what we can say is like Schottky barrier. Earlier it was, it was named as a hot carrier. Later it was, changed into the Schottky barrier and all. So the Schottky device also known as the Schottky barrier diode. Only introduced, and they only invented this thing. So in the at that time only, they have actually they have worked papers also in the hot electron triode structure with the semiconductor metal emitter. So these are the things, like how the journey started with the. We will start our the things like nanotechnology. So this it was the motivation behind in whoever is working in this particular research, who want their career in technology or nano research or nano-electronics. So we should have like some history. We should have to know like how people very much, and then they came in the picture. So these were the these are the motivation which we can say. So definitely this how this start at the time. Feynman also in his speech, like there is a plenty of room at the bottom, which is known as the origin of the nanotechnology. And it was actually in the 90s only it was discovered. Okay, see what happened till 1960 only they have discovered, and they did all the things. But till 90s actually it was, nobody bother, or you can say that this nanotechnology, actually not much people, they have given the more focus on this particular area. So that's why this nanoscale science or nanoscale engineering, it was little back. And after that in 1990s only, all the people, they have started working on these things, like when the computer came into the picture. So after that it actually catch the pace, and then finally the breakthrough happened. So well, will not discuss much, will not go the history of these things in too much. Okay, so we are coming to the nanostructure. What is basically the nanostructure, what is nanoscale, and how this nano structure, it is different from the thin film. And what are the application associated with this nanostructure? That we will see. So out now, is it okay?
It's going very well, ma'am. You can
Anybody's
proceed,
there?
ma'am. Yes, ma'am. You can
Okay,
go.
okay.
You can go ahead, ma'am. It's going very well, ma'am. Very smooth.
Okay. 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 Thank you. So, any participant is having any doubt or any research area or something? Definitely, I'm going to discuss all the research gap and all the research area which is related to our nanotechnology.
We have a query session, ma'am. At the end of the session, we have a query session, ma'am.
Okay.
Participants will be posting their queries on the chat box, ma'am. So we'll have a discussion at the end, ma'am. That's not an issue.
Okay, okay. So in between also, if they are having doubt, they may ask.
Yes, sure, ma'am. Sure, ma'am. Sure, ma'am.
Okay, okay. Thank you. Behind any nanotechnology researcher, I mean, any researcher who is working on this nanoscale or nanotechnology. So I would like to say, I mean, like, do you mean by nano? So nano, general meaning is dwarf, okay, which translates as a little. Okay, so it is a whenever we are dealing with a very small range or in a nanometer range. Okay, so
Ma'am, can you switch into PowerPoint presentation mode, ma'am?
if any device we are going to make in a nanometer range, so definitely it will be called as a nanostructure. Yes, pardon, sir.
Can you switch into PowerPoint presentation
Full
mode,
screen?
Yeah, ma'am.
Achha, it is okay. 1 second. Is it visible?
It is in normal mode, ma'am. If you can switch over to presentation mode, ma'am, that will be good. Yes, it is visible, ma'am, but you are in normal mode, ma'am. If you switch into PowerPoint slideshow mode, means it will be good.
Only I did. Full screen only I did.
Okay.
Maybe the poor call quality.
Yeah, it's right
So
now. It's good now, ma'am. It's okay now, ma'am. Thank you.
No, it's okay. Okay. Thank you. So the structure which is in the nano meter range. Okay, so nanometer range, or you can say like 1 nanometer to 100 nanometer. If the scale belongs to a dimension belongs to, so it is called as a nanostructure, or you can say whose structure elements are cluster or crystallite size or molecule which is in the nanostructure, right? So in the nanostructure thin films, the electrons and they are free to move in that particular direction only. The types of nanostructure. Okay, so type structure, that means 0D nanostructure, 1D nanostructure, 2D nanostructure, and 3D. Okay, so 0 D nanostructure, that means system confined in the tension. Okay, like electron are there, so they are confined in all the 3 directions. They are not. I mean, they are not to move in any of the directions. it is a 1D nanostructure, then in the one dimension only, whether it is X dimension, Y or Z or any dimension like vertical, horizontal. So in one dimension only, this our electron, it may move, and in the another 2 dimension, these electron, they will not able to move in, they are confined. Okay, and the two in the 2D nanostructure, so that means the 2D definitely, in the 2 dimension move, and 1 dimension it will be kind of 2D. Generally 2D nanostructure, they are nothing but the nano, what you can say, it means we are having the thin films kind of nanostructure, and then in the 2D nanostructure we are having like nanorods are there, nanotubes are there. So these are the example for our 2D nanostructure. If I'm talking, so in all the dimension, the electron, okay, like nanoparticles are all, these are for the example of our nanoscale nanostructure, types of nanostructure which actually they are existing. So techniques, generally, I mean, if I'm talking about the types of nanostructure, so definitely be having different applications. So all the nanostructure cannot be like nanorods are there, nanotubes are there. So they are actually, they are very good for the UV application. Okay, or you can say these are electronics, like then 3D particle, these are also very much beneficial for this optical applications. It is not mandatory that 1D nanostructure will also be applicable, right? So all the different nanostructures, all the nanostructure, they are having a different application, and according to the application only, we are going to grow this particular nanostructure. So many factors are involved to grow. For example, if the one provide for the growth of particular nanostructure, it can be completely different from one D nanostructure growth, right? Structure can be grown in a different field. So it is not like generalized terms are not like 0 nanostructure or 1D or 2D or 3D. They are having the same environment for the growth purpose. No, not at all. And they are not having same application as well. So according to application, we are growing, different we need to apply for growing the. So we can see the application, or we can have so many like its applications are only the future scope, like range. If I'll see like reflective, inference filter are there, memory disk, waveguides, beam splitter, decoration. These days, so many things like in the are also coming into the, so graphene based. These all are the application in the field of optical. And when we are going for the optoelectronics, so these days the solar cells are, what you can say, everywhere solar cell it is there in the market. It is just like a hot solar cell, photo detector like UV photo detector, or other depending upon the wavelength of the particular material and device. The laser device, so just there. I mean, so many other applications are there. So going for the magnetic recording media, sensors. So when we are coming for the electronics, so printed electronic device or flexible electronic device, TFTs are there, LCD, OLEDs, semiconductor device, like what you can say the Schottky diode, right? Schottky diode and some structure. So many things are there for the electronic devices. Then we are having the sensors like gas sensor, we are having the biosensors, we are having like these days glucose sensor, the blood sensors are coming into the bio sensor. After that, so many these days like antimicrobial properties also we can get through these sensors we can do so, and gas sensors like any gas like ammonia is there or helium is there, any gas it can be sensed with the help of gas sensor. So in the engineering or processing, so that also we can do with the help of this nanostructure devices like protective coating and low friction coating to reduce the wear, corrosion and erosion. So these are the many applications on which this nanostructure device we can go for. So whenever we are talking about the optical things or optoelectronic things or sensors, so we are having so many semiconductors material with wide band gap. So we are having so many things like zinc oxide material we are having, gallium nitride we are having, zinc selenide we are having, zinc solenoid we are having, so zinc sulfide we are having. So many materials, so many semiconductors we are having in market by which wide band gap semiconductor we are having, by which we can actually make the nanostructure. So see, so many other materials are also there, but these are the materials by which we can actually, first of all, these are having wide band gap. That is the most important point whenever we are working on the optical field or whenever we are working for the optoelectronic field. So these are the things, these are the semiconductors which we are actually going for. Like wide band gap semiconductor we require. Okay, so with this we are having this energy band gap like 3.37, 3.4. The more the energy band gap, it is better for our optoelectronic property. Okay, so excitation binding energy, that means the minimum amount of energy we are giving so that the electron can leave the the valence band and it can move. So that is called zinc oxide have strong excitation binding energy. Then dielectric constant also we are having. So by which we have specified like 4 or 5 material semiconductors by which we can actually create the nanostructure. So these material actually help to grow the nanostructure in a better way, in a very different manner. Okay. So as we are having so many band gap, so in which we can take, see, like this is zinc oxide and gallium nitride. These days, these are the more demanding, or you can say the most promising material. Okay, by which, in which, like zinc oxide is better, it is not better, but quality-wise, see, gallium nitride is better, but we have to see the cost effective as well. So whenever we are going for the commercial purpose, so we need to check the whether it is a commercial, whether it is a cost effective or not. Okay, so whenever we are seeing these things, zinc oxide, it is a very cheap compared to gallium nitride. So because of that particular thing, we are actually going for the zinc oxide. So first of all, I just we'll see the zinc oxide that is widely available. So as any material is widely available, definitely it will be a cheap. And the plus point is it is a non-toxic as well. So these are the very much beneficial points. And direct and wide band gap it is having. So wherever this direct and wide band gap, that means directly it can be applicable for the optoelectronic properties. Like immediately we can apply in the LED, laser diode, photodetectors, anything. Like optoelectronics, this is actually made for the optoelectronic application, this particular material, if it is having a wide band gap and direct band gap. Okay. Next one, it is having a very high exciton energy. That means it makes efficient light emitter as compared to gallium nitride. See, earlier what I was telling you, gallium nitride was little better in terms of wide band gap, like 3.4 it is there, and lattice parameter and and this dielectric constant. But the thing like excitation binding energy, it is zinc oxide, it is having a very high excitation or exciton binding energy, which makes it's better than gallium nitride, and that is favorable for optoelectronic application. Okay. Next one, it is electron mobility as compared to amorphous silicon and low processing temperature as compared to, so that's why. So it is having high mobility also. So whenever we are going for the electrical parameters, so generally whenever we are making any device, so we are actually dividing into the 4 parts, like structural parameter, optical parameter, then electrical parameter. So these are the things by which we can actually divide our material. Okay, so see, optical property, it can be identified with the help of direct and wide band gap. After that, electrical can be seen by the mobility factors and high binding energy, and with the help of fabrication technique, we can get the structural properties. So these are some of the properties of the zinc oxide. And these are the applications of zinc oxide nanostructure device, like what are the things we can make with the help of, if we are able to grow this zinc oxide nanostructure. So we can apply in different fields like devices, data storage, photodetector, LEDs, transistors, biochemical or chemical sensors. So these are the variety of applications. So as these things are there, so we can easily tell like a zinc oxide nanostructure, or you can say zinc oxide, it is a very it is having a very high potential, or it is a very promising material for transducer devices once it being made in the fields, depending upon the which kind of dimension it is having. Okay. So it can be applicable for the UV detector, it is applicable for solar cell, it can be applicable for laser diodes, it can be applicable for transistors, cantilevers, sensors, anything. Okay, so scope to tell you how, first of all, it can be fabricated. Somebody wants to pursue their PhD, or somebody wants to pursue their career in the fabrication. So how it can be done in a further. So fabrication, I mean, how this fabrication can be done in the zinc oxide nanorods, and then how this, I mean, definitely what is happening, only single material we are using. So we can dope this particular material, some structure are same ionic bonding. So and this heavy mobility. So definitely, okay. So that doping also we will discuss. After that, I mean, we are having only like Schottky contacts or ohmic contacts. So we will discuss the different contacts also with the different structure. So these are the scope of the present. See, so it can be seen like just a fabrication and characterization of zinc oxide nanorods with the gold palladium contacts. Okay, so this is actually it has been fabricated. So first I will tell you the what is actually the Schottky diode is, and then we will go for the further fabrication, that how this fabrication it was done. Okay, and by which technique we did, and what I mean, what are the things already done, and what are the things we can do in the future, so that I mean you can publish I mean nice papers in the journals and all. Okay, so we are having like Schottky diodes. So Schottky diodes, so I think each and everybody would have known about the Schottky diode. I mean, if you are, I mean, if you are doing like simple BTech also, or in the UG, PG, PhD, everybody would have known the Schottky diode. But how it is being fabricated, that is, I mean, I think very few people would have known. Okay, how this junction is being I mean created with, I mean how this IV characteristics it is coming, and what are the factors involved while calculating the electrical parameters. So all the things, everything it is involved. Okay, so Schottky diode, or you can say it is a junction between a metal and semiconductor with some rectifying properties. Here, like Schottky contacts we are having, and ohmic contacts in semiconductor normal silicon substrate only we are taking, and over that we are depositing the semiconductors, and after that Schottky contacts we are creating. So Schottky contacts, so I mean definitely you people must be thinking what is the difference between the Schottky contacts and the ohmic contacts. Right. So that will mean how it is different from, I mean, what are the advantages? Charge storage effect, it is minimum, or you can say it is a very effective in the high speed digital circuits. Majority pointers, it is there. Okay. So that only we are talking, like, I mean, how it is different from the Schottky context, how it is different from the ohmic context. So the work function, the metal work function of this Schottky should be greater than the electron affinity of the semiconductor. Okay, for example, if I am if I'm using semiconductor, for example, zinc oxide semiconductor I'm using. Okay, so for that purpose, if I want to fabricate any contacts such as Schottky contacts, if I want to create, what I need to use is like platinum, palladium, or gold, or iridium. So these are the materials having a higher work function than our zinc oxide, because our zinc oxide, it is having a 4.5 electron affinity. Okay, so that's why we need to use in order to make the Schottky contact. If I want to use the what you can say, the ohmic contact, then I have to go for the aluminium. Okay, aluminium or copper. These are the material which is having lesser work function than our zinc oxide, having approximately it is near about 4 electron volts. Okay, so this is the difference between our Schottky contacts and ohmic contacts. Okay, so applications are so many wide application of our Schottky diode is like gas sensor, UV photon detector, field effect transistor. Okay. So these are some methods for reducing defects in the things. So what are the research gap? Okay, research gap, or what are the challenges, or what are the limitations when we are going to use zinc oxide thin films, is the defects in the zinc oxide thin film and the interface defects between the thin film and the metal contacts. Okay, so how it can be reduced? By using the annealing effect, or you can say by inserting the buffer layer in between the thin film and the substrate. Okay, buffer layer is nothing but, for example, if I want to fabricate, or if I want to deposit any semiconductor layer over the substrate, so in between the substrate and the main layer, we need to deposit a few nanometer, like 1 to 100 nanometers things only. We are actually depositing in between the main layer and the substrate, so that the lattice mismatch, it can be avoided. Okay, so inserting a buffer layer, okay, and choosing a proper method for thin film deposition. So proper method or proper technique is also very much important whenever we are going to fabricate any device. So we have to have a proper technique. Okay. And then after deposition also, we can anneal the things so that it can grow accordingly. Okay, so these are the, this is a very simple flow, design flow, or you can say the fabrication this is a design flow by which we could fabricate a Schottky diode. So first of all, we have to take N-type silicon substrate or P-type silicon substrate depending upon the application. Okay, as I am going to make this Schottky diode, so I am using actually here N-type silicon substrate. Okay, so if I am going to make the heterostructure, so definitely I'll make the P-type silicon substrate, because zinc oxide, it is having inherent, it is N-type quality. Okay, so accordingly, according to your semiconductor, that kind of substrate you need to use. Okay, so N-type silicon substrate. So before, as we are going to fabricate, so before fabrication of any device, we need to clean the substrate first. Okay, generally substrate we are purchasing from the market itself. So it's actually, whenever it is coming into the air, it may contaminate. Okay, it may oxidize, it may contaminate with so many organic or inorganic materials available in the air. So before fabricating any device, we need to clean. and that too we need to clean with the help of RCA cleaning, RCA1 and RCA cleaning, followed by the HF cleaning method, that is the hydrofluoric acid. So these are some very important steps prior to deposition we need to do so. Okay. After that, as I told you in the previous things, like we are having, see, you can see in this highly affected by defects and intercepts. Okay. And method of reducing, so how we can do, by inserting a buffer layer. So here only it can be implemented, like before growing the main layer, before growing the nanostructure. What I did was I have actually incorporated, or what you can say, I have deposited the aluminium doped zinc oxide seed layer or buffer layer, both are same. Okay, some people, some researcher, they are using seed layer, some they are using the buffer layer. So with the help of inserting, or with the help of fabricating one seed layer, what is happening, the earlier what will happen, if directly the main layer, if I'll deposit onto the silicon substrate, and if directly deposit this silicon substrate and the main layer, what will happen, there will be a large lattice mismatch in between the main layer and what you can say, silicon substrate. Okay, but right now what I did, I have deposited a very thin layer, that is a 50 nanometer layer in between the silicon substrate and the main layer. Okay, before depositing main layer, I have fabricated, I have deposited over here. Okay, with the help of this 50 nanometer layer, what happened, this nanostructure can grow very nicely and very effective. Okay, the growth rate as well as the structure, the alignment, everything, it became very much okay with the help of single thin seed layer or buffer layer. Okay, so here I have incorporated one aluminium also into the zinc oxide. What happened, the mobility of aluminium high, so that is going to contribute into the electrical behavior of. Okay, so what happened after that, this structure we have deposited over the silicon substrate with the help of RF. After that we have palladium alloy, okay, over these nanostructures, so that here, I mean, upper side we can take as a anode, and back side, aluminum we have deposited. So aluminum we will take as a ohmic contact, and here we will take as a Schottky contact, or you can say anode. Okay, so before before depositing this metal, before doing this, after growing this nanostructure itself, we are distributing. See, at one batch we are not fabricating, we are actually fabricating different devices, 4 to 5 definitely 4 to 5 devices we are actually fabricating in a single batch. So these we are for this, what you can say, like structural properties. Okay, like XRD we are sending, and then SEM and AFM we are sending. After that we are sending for this ellipsometer for optical behavior, and then after that we are doing the metallization, and then we are going for the electrical behavior. Okay, so these are the, that's why we have to make like 4 to 5 devices at the same time. So these are the energy band diagram for the Schottky diode. So the if I'll you can see over here, like XRD image, like with the help by using simple buffer layer. Okay, so by using the buffer layer, how the structural parameter has been changed. Okay, like single crystalline structure, it can be seen like 002 at 34.29. So at this point, if it is coming, the structure, I mean the graph is coming like this, that means it is a single crystalline. It is the device is showing the single crystalline nature. So it's single crystalline nature, that means definitely it is oriented toward a single direction. Okay, so it is I mean the structure is very good if it is showing like this, and the crystallite size is also bigger, and the interplanar spacing in between, the interplanar spacing, that means this distance in between the two molecules are too crystal. Okay, and the strain is also very less. So XRD, like X-ray diffractometer analysis, so it is actually giving the crystalline nature of the, or you can say the structural parameter of your this is the top side view of a zinc oxide nano rod on the silicon substrate. You can see over here, the first one is a seed, like aluminum doped zinc oxide buffer layer only we have deposited. So it is looking like this. Okay, when we are dealing with the 1 micrometer range, so it will look like the scale will be like this. After that, when it is the zinc oxide nanorods, it has been grown. So you can see like a round structure, it is completely round kind of structure, it is it has grown. And when we will see this cross sectional view, so cross sectional also, you can see the it is easily visible that nanorods are being fabricated, and it has been grown on. Okay, and these are the SEM images and SEM AFM images that make force microscopy. It is actually giving the roughness of the device. And then we'll find out the band gap. So it is done with the help of ellipsometer, and this it is showing the reflectance and transmittance, and then we need to find out with the help of formula, and then we need to extrapolate this in this band gap. So reflectance means how many percent light it is being reflected back. Okay, so we can see like very less amount of the light it is being reflected back, and most of this it is being transmitted. Okay, so that's why it is a wide band gap, and it is very much useful in the optical you can say optoelectronics application. After that, gold palladium alloy, it has been deposited, and then finally we have we have characterized the anode. So you can, it is result, and this red line, it was showing the simulations. So simulation, it was done with the help of a software tool. It was available. So with the help of those things, and it was a comparative analysis with the simulation and experimental. So with the experimental, we can say height, it was with this formula only, like here I is equal to I naught QE upon E. So with this only we can calculate the phi value, and then IL factor also we can find it out, and the rectification ratio is nothing but I on to I of ratio. Okay, that means in the forward and in the reverse current ratio, and then reverse saturation current also out. So we can see the simulation result and experimental result, they are almost, not equal, but they are in the range. So this was the validation in between the experimental and simulation result. Okay, I mean in analysis what it was done and all those things. Okay, I am just giving a brief that it can be done. Okay, and then this is the electrical behavior. So I mean nicely you people can go for the UV detection if simply oxide is there. So definitely like in the zinc oxide easily we can do the UV detection and that is UV light. It is in the easily we can UV light and we can get the this what you can say we can get the UV sensor. Okay, that this particular device it is responding in I mean in the visible range also you can get. These are the things are you can apply because you can apply this particular device into the gas sensor as well or biosensor as well. So many applications are there which can explode with the help of this particular device. This is a very simple, very basic device, but so many applications are still there, okay, to do so. So next one is the technique. What I about in the first in this particular slide itself. This particular slide itself, I told you methods for reducing the defects. See, first thing I have, I have cleared that introducing or inserting a buffer layer in between the main film and the substrate, so it can reduce the defects. Okay. Second thing, choosing the proper method for the thin film deposition. So my next paper will be on this particular which technique be followed and technique we should have in order to get or you can say the optimum efficiency of that particular device. Okay, so here we like complete as deposited zinc oxide thin films by actually we are having two types of method like chemical method we are having and PV physical vapor deposition, laser deposition we are having, RF sputtering we are having. So we have deposited this particular zinc oxide thin film in all the device in the silicon substrate with all the techniques, and then we have found which technique was the best. Okay, so here also we have taken the silicon wafer over which we have deposited the 150 nanometer zinc oxide layer, over which we have deposited like palladium and aluminum as a Schottky and ohmic contacts. Okay, like on the top also we can deposit, or on the back side also we can deposit. There was no issue. So with the help of those things, what we found, you can see like the downside image, you can see like the actual image of the gold palladium zinc oxide RF with the first one is with the help of RF sputtering, then with the PLD, and then with the thermal evaporation. So by seeing the substrate itself, the more transparent the substrate looks like, the more what you can say, the quality of the depositing layer or quality of the layer, it will be very good. Okay, so as you can see over here, the RF sputtering process substrate, the A, it is looking very transparent and blue kind of color, while this PLD process, it is little the shine, it has been reduced. And when we are talking about thermal evaporation, so the shine almost went out and it becomes like a grayish color. Okay, so the quality, the deposition, the quality of that particular thin film, it has been degraded. Okay, I have not included all the diagrams and all the structure and optical things. I'll discuss the things like how it has been changed from. You can see with the naked eyes also we can see like it is very shiny, and then the shine has been reduced, and then it is even lesser. So the quality of the thin film deposited under the silicon, it has been reduced, okay, or it has been degraded. So what we can, from this particular diagram or this particular image, we can easily say that RF sputtering method, it is far better. Because how we can conclude? On the basis of deposition, or you can say on the basis of the quality of the film which has been deposited, on the basis of that only we can say that our device is going to be good or bad. Okay, so RF sputtering, if we are using the RF sputtering method for depositing any layer, so definitely it will be very good. Okay, so see, with the help of this diagram image only I told you, and when we will go for the IV characteristic, or when we will go for the electrical behavior, so you can see over here also, like in the electrical behavior, like black one is the RF sputtering, red one is the PLD, and the green one is for the thermal evaporation. So from here also you can see the black one is the zinc oxide deposited by RF sputtering. Okay, it is showing the ideal characteristic of this PN junction diode. Okay, and others are this PLD, I mean deposited by PLD is also showing a good behavior, but deposited by thermal evaporation, it is showing a very bad electrical behavior. So we can say that RF sputtering is the best technique by which we should have to deposit our device. Okay. So till now what we have discussed, that by using the buffer layer, the interface and the quality, it can be improved. By using the best technique, we can improve our device quality, and we have seen in the electrical behavior also, like RF sputtering was best for depositing any layer. Okay, these are the two things we have deposited. Now now we will go for what you can say. Now we will go for the incorporation of any material, or incorporation of any element in our film, so that it can be the behavior of electronic application, it can be improved. Okay.
Excuse me, ma'am. I think your screen is not visible, ma'am.
Screen is not visible?
Yeah, it's now visible, ma'am. It's now visible.
Visible?
Yes, ma'am. Yes, ma'am.
Please let me know, because I'm speaking and I don't know what is going on.
I'll be there, ma'am, to make a note about this. Yes, ma'am. It's now visible.
Now visible, na?
It's visible, ma'am. It's visible.
Okay. So different conductor can be your optical and visible. So likewise, I told you, like aluminium, we have deposited in the zinc oxide buffer layer, so it has improved the device characteristics, like the structural property, optical property, it was improved. So here also we will see like what the effect of magnesium concentration in zinc oxide buffer layer it can incorporate into the electronic application. Okay, so whenever we are going to incorporate any material like magnesium to zinc oxide, what it will be done? So first of all, why magnesium only? Why not another material or something? Because see, if I'm going to we are dealing with the electronic application, so definitely we want to improve our optical behavior. Yes, So optical behavior, because as magnesium is already, it is, say, zinc oxide material, it is having the 3.4 electron volt, 3.37, okay, but the magnesium, it is nearby 4 to 4.2 electron volt band gap. So definitely it is going to enhance the band gap or optical behavior of the material. Second things, the ionic radii of our magnesium ion, it is similar to our zinc 2+ ion. Okay, so the ionic radii are also similar. So it is easily, it can accommodate the zinc 2+ ion site, and the structure will not be changed. Okay, because when we are dealing with the nanometer range, or when we are dealing with the lesser than nanometer range, these things will came into the picture very clearly. So it should be accommodating in such a way that our lattice structure or the basic behavior of that particular material, it should not change. Okay, by keeping the basic property or by keeping the lattice parameter constant, we need to enhance the our optical and structural and electrical behavior. We should have to keep in mind always. Okay, generally what people are thinking, okay, the high quality material or high efficient material, if we will incorporate into our zinc oxide, then what will happen? So we need to keep in the mind that we have to keep our structural property, or you can say the lattice parameters and crystalline size the same, okay, and we need to enhance those, not compromise with our lattice structure. Okay, so here that's why we are using, so we have to more specific whenever we are going to what you can say, whenever we are going to choose any material like magnesium or aluminum or anything which we are going to incorporate into the zinc oxide. So at that particular time we have to be very much careful, okay, which kind of material we are going to use and what effect it can give, because when we are dealing with the fabrication, we have to focus on our cost effectiveness also, because in the simulation what we are doing, one-time purchase we did, okay, and then we are simulating the things, but in the fabrication we are dealing with the real life world. Okay, we are not dealing in a virtual world. So in the real life world, what we have, for example, if we have deposited any material over a silicon substrate, okay, and we have metallized. So what happened? First of all, we have, we use that particular technique. For example, RF sputtering we have used. Okay, so RF sputtering, power supply, and material, and the gases related to RF sputtering. These are the basic things. Second things, we have cleaned the silicon, and silicon also we have used, that is also wasted. Okay, after that we have used the materials like zinc oxide material, and we have incorporated so many material into that. So so many materials as well as effort and time, these are the things we have to keep into the picture. We have to keep in our mind that it should not be wasted. Okay, so we have to be very much, we have to, first of all, we have to gather all the literature. We have to calculate each and everything. We should have to make note, and then we are going for the fabrication things, right? We are not jumping directly into the fabrication field, and we cannot afford hit and trial method. That is the main thing. Okay, so after that, we are seeing the effect of magnesium concentration, how it is going to affect in our zinc oxide buffer layer for the electronic application. So in this particular thing also, what we did, we have taken the silicon substrate over which we have deposited the magnesium doped zinc oxide layer, and this time I have magnesium, I have doped like 0%, that means simple zinc oxide 1%, 2%, 3%, 4%, and 5%. Based on the literature only, we have incorporated the magnesium oxide into a zinc oxide powder manually, and then we have made the tablet, and then we have fabricated. So it took a very hard work also manually. So we have made the tablet and then fabricated. Okay, so 0%, 1%, 2%, 3%, 4%, and 5%. That kind of things we did. Okay, so this basic structure we have created, like the silicon substrate, and this was the this a little layer, this very thin layer, that is a magnesium zinc oxide buffer layer, and then thin film, and then over that gold palladium dots, or you can say gold palladium alloy dots, and this aluminum dots. And by using what happened by incorporating the things, when it was done without doping, and then 1%, 2%, 3%, 4%, 5%. So what we have seen at the 3% of this magnesium doped zinc oxide buffer layer, we have, I mean, our structure, it is, this is the final, the upper layer. So this shows a very nice and smooth curve, and after that we are not getting much, and before that also, after that also, we are like 2% also it is acceptable, but 3% we are getting the best result. So at 3% we are having the FWHM, the best FWHM, which is the full width half maximum light lattice constant, the crystallite size, and strain is minimum. So strain is also plays a very much important role. That is, if you want a nice and a very good thin structure, so definitely your strain should be very good. I mean, the strain should be minimum as possible. Okay, so these are the things. So with the help of EDX, we can find out like which film is having what material or element. And these are the same image, that is a scanning electron microscopy. So 0%, 1%, 2, 3, 4, and 5. So AFM image. And this is for what you can say the reflectance, or you can say the band gap. So you can see very easily that is blue color, 3% magnesium. It is having the high band. Near 3.7 electrons, because after 3% into the zinc, it is degraded out. Ideality factor, that means how the device is ideal towards the, I mean, this our device is ideal. That is called the ideality factor. That means how it is following the ideal behavior of any device. Okay, so that is called the 3 at 3%. It should be nearby 1. Okay, so it is the minimum we are getting. That is the I on to I of ratio. That means when we are giving a power supply, this series resistance is. Okay, so these are the these are the things at the 3% of the measurement. So with the help of these things, we can make the UV detector or differently. We can use the see, till now we have used the PN junction diode, or you can say the Schottky diode, these kind of things. But some other devices are also there. For example, MSM structure is there. Okay, so in the MSM structure, definitely we need to like interdigited contacts we need to do. So if we have to do the interdigited, so this metal semiconductor metal structure can be viewed as a two Schottky diode structure connected back. And how it is better? Because it is having a more planar structure, and whenever we are going for the fabrication, we are seeing for the more planar structure than any other structure. So it is easy for fabrication and simple structure and integration technique and low capacitance per unit area as well. Okay, so this was also one of the proposed structure we had, where we use the silicon substrate P-type and then zinc oxide buffer layer. And then as in the previous work, we have seen that 3% of the magnesium zinc oxide was the best thing for the optical and electrical characterization. So at this particular point, we have taken a 3% magnesium doped zinc oxide in the main layer also. Okay, and here we have changed the buffer layer, like a very normal buffer layer we have used, like a zinc oxide buffer layer, and over the 3% we have seen. And then finally we realized that our XRD image is extremely well, and it is well aligned in that particular C-axis orientation, that is 002. And with you can see over here like a very nice, and I mean what you can say, very nice and very I mean the growth, you can see very uniform growth it has been. We can see like this is a nanoparticle structure, it has been grown. Okay, so with a different pressure and with a different temperature, we have grown this nanoparticle things. And you can say the AFM image is also how uniform, how beautifully it has been grown over the entire substrate. Over here with the, I mean, you can, and we have, we did a comparative analysis also, like with simple zinc oxide silicon, and with the help of 3% magnesium doped zinc oxide over zinc oxide silicon, how it has been changed. So our size it has been improved, roughness it has been decreased, and total roughness it has been decreased. And when we will go for the optical transmittance, so optical transmittance also we can see that transmittance it has been increased, reflectance it has been decreased, and the optical band gap also it has been increased. And this was the interdigited mask. When we have interdigited mask, and with the help of the SEM image only, we can see like from upper side you can apply the UV light, like 365 nanometer wavelength UV light we will apply onto the MSM structure. And so then when we applied into this nanoparticle, then what it will happen. And we did a simulation as well with this, with the help of Atlas Silvaco only. And these are the models we have used for the drip diffusion and standard recombination for Dirac and all those things. So these are the simulation and what you can say, like experimental results. We are having zinc oxide thin films in the dark and in the light. So here in the next slide we can see the comparison in between the magnesium zinc oxide nanoparticle grown on the zinc oxide buffer layer coated P-silicon substrate. So these are the simulation, and this blue is the experimental when this light was off, when the light was on, and when the light was off, then these were the results. So these are some of the formulas. With the help of these formulas only we can find out all the these electrical properties, and this finally the contrast ratio, the responsivity, the quantum efficiency, detectivity. So with the help of these formulas only we can find it out. Okay. So this is what for the experimental and this is what for the simulation. And these are the, the physics behind how the UV detection it can be done. So in the, you can say it very easily like UV detection in the under the dark region and under the light region, how it will be done. So in the dark region, what it is doing, UV detection, see, we are having, whenever we are dealing with the nanostructure, so nanostructure, generally, why we are using this nanostructure for sensing properties or UV sensor or biosensor or gas sensor, why? Because it is having a large surface to volume ratio. Okay, as we are dealing, as it is having a large surface to volume ratio, so definitely more and more atoms it can attach. Okay, it will be absorbed and deabsorbed. Okay, so here what is happening in the dark condition, only O2 is there, oxygen are there. So first oxygen it is going to absorb the electron and it is becoming the O2 minus. Okay, and whenever we are giving the UV light which is greater than the value of the H nu, so what will happen, this this light will be there, and this light it will combine the proton, it will combine with the O2 minus, then it will again deabsorb and finally O2 layer will be there. Okay, so this is the physics behind the any UV detection characteristic if we are going to use the nanostructure with and without illumination. Okay, and these are some comparative analysis. If we are going to, this is first one is our proposed device in which contrast responsivity and quantum efficiency detectivity we are having, and these are the other other structure by which they have got. So we can easily see over here like we are having a better contrast ratio, responsivity is also we are having okay, and the quantum efficiency also we are having somehow okay, and detectivity is also we are having good. So likewise we can see. So these are the things which we have done till now, and heterojunction structure also we can make with this only. And with this, these are the things we have deposited and we have fabricated, and these are the things we are working till now. And some future scopes are also there, like we can make the photo detector, I already told you, with the help of the Schottky diode or PN junction diode. Or other than this, if we will see, so we are having the, we can see the solar cell. These days, I already told you in my very first slide, like solar cell, it is these days, these are the hot cake. Okay. And that too solar cell, see, earlier we were making the solar cell on the silicon substrate. Okay. So on the silicon substrate, but these days we are having the perovskites. It came into the picture. So it is a combination of organic and inorganic material which is having a very cost effective. So because whenever we are going for the commercial purpose, so we need to see the whether it is a cost effective or not. Okay, so so this whenever this till the time this perovskite it came into the picture, it is actually boom in the market. And it is a very promising because it is a combination of organic and inorganic. Only the thing is we need to see the efficiency and stability. Okay. So generally till now, if we will see the silicon solar cell, we are having like 20 to 25% efficiency only we are having till now, but 20 to 25% efficiency till now. So by using this perovskite tin lead iodide perovskite material, and by using the methyl ammonium, so we can enhance the solar cell efficiency and the stability. So here we can see some of the papers we are having, like this is only the solar cell, organic solar cell. So this paper, if you people want, I will share these people. Like this is the recent work, and it actually published in 2020 itself. Like just now it has been published in the Nature Energy and the two. So you can see over here, like these are the structure they have created on this perovskite film only. So tin and lead. So these are the basic structure, how they have created and how they have grown the things by after annealing. So this is upper layer, lower layer. You can see the SEM image also, XRD image also.
Excuse me, ma'am.
Yes.
It's not visible, ma'am.
Achha, screen is not visible.
Yes, yes. Yeah, it's
actually visible.
Yes, ma'am.
Visible.
Yes, ma'am. Yes, it is visible now, ma'am.
Okay, thank you. Maybe it takes some time to change. So yes. I'll show you, first of all, I'll show you the device structure. So by which this perovskite film we can, we can deposit it. So this, see, we are having two techniques, like having the PVD technique, CVD technique. So CVD is a chemical, vapor deposition, and the PVD physical vapor deposition. So chemical method, that means we are having the sol gel and all other materials. Electrochemical analyzer is also there. So these are even the cheaper than these PVDs. So it can be done with the, if a small sol gel, if you people can purchase in your institute or something, easily this solar cell, it can be fabricated. And for the characterization purpose, you can send your sample to any institute. So there will be no problem for this XRD and SEM images. And after that, we can finally we can find out these things. And then electrical field differences also we can find it out. So very, this. Then finally, open circuit voltage we have they have calculated, and then efficiency they have calculated. And then efficiency versus wavelength graph also they have plotted. So these are the see. So what I would like to say is, we people are thinking that nature, for publishing the paper in IEEE transaction, and the nature, it's very tough. No doubt it's tough, but it's not a miracle kind of thing. We can see they have normally they have fabricated with the help of sol gel. They have annealed with the different temperature, and then finally they have grown, and then finally they have given for the characterization. So only the thing is, like, we have to clear with our vision. We have, the problem statement, it should be clear so that we can go. So this is one of the example or one of the research gap you can work, like efficiency these days, efficiency and the stability. These are the two things. Because solar cell, if we will get efficiency also after what you can say, after 10 days, 20 days, 1 month kind of things, stability will not be there. The same efficiency what we were getting at the day 1, we will not get at the day 30th. Okay, so we have to make our solar cell in such a way that efficiency and stability will be maintained. That can be one of the problem statement. Okay, these days we are we are working for this wideband terahertz absorber, like in the initial also, like our principals are told, like after gigahertz, when we are going for the terahertz and all the these mixed signal design and all these things, it will come into the picture. So wideband terahertz absorber also we can make. Okay, so here, I mean, in this particular diagram, you can say like our we can actually introduce the graphite disc resonator in between these absorber. Okay, and it is the graphite dielectric cavity resonator based absorber. Actually, they have analyzed and implemented, and right now we are going to work. Actually, he is one of my colleague only, and he is he has simulated this particular thing into the CST. Okay, so CST and ADS software. So with the help of that electrical I mean, they have he has made this particular graphite ring and substrate and graphite sheet, and now we are actually we are planning for this, for the fabrication also for this thing. So you can see like he has calculated frequency versus this responses, actually reflectance and phase and absorption he has calculated. So this is only simulation thing. So you can see, so in the nanoscale only we are going to work, and we can, I mean, this is the simulation work. So when we will fabricate particular, see, this is in the IEEE sensor journal. So when we have simulated only, then it is in the IEEE sensor journal. So when we will fabricate and we will do the comparative analysis in between the simulation and the, what you can say, the fabrication. So you can think like in which journal it may go. Next, I mean, some papers are there. Like we can, I mean, reflector in the optical filter application only we can do. And after that it can be I mean, absorber itself, it can be done. Solar cell, it is over. Next one, it can be it can be used in the laser action also, lasing action in a single sub wavelength also. It can be we can see like this kind of I'll show you this kind of diagram also we can in place of gallium arsenide. Just now we have seen like we are having a better material and even a cost-effective material we are already having. Like for example, we are having zinc oxide. So in place of gallium arsenide, we can use our zinc oxide, and after that we can fabricate these things. So these are the scattering, I mean, simulated characteristic of a single gallium arsenide nanocylinder. So in place of gallium arsenide, we can change the zinc oxide, and then we can make a nanocylinder. So this is a simple simulation result. So when we'll go for the fabrication, you don't know, I mean, how far you will go. So these are the FWHM and simple lasing effect, lasing threshold. So optical characterization they did, and after that we can go for the nano fabrication also. Like you can see over here, like gallium arsenide 500 nanometer, aluminum 100 nanometer, undoped gallium arsenide. So these are the basic structure we can make on a simple wafer of a quartz substrate, or simple glass substrate also we can do so. And with the help of these things, we can actually, when we will fabricate, so we can apply in any of the field. After that, eco-friendly approach also, anti-bacterial effect also I told you, like how it can be applied. And so antioxidant, or you can say like in a bio sensor also we can use. So only the thing is we have to, I mean, study more and more. We have to update ourselves more and more so that we can go through these things. And I hope I would have delivered some of the, I mean, research gap and some of the future scope to all of you. So with this, I would like to finish my PPT and presentation. I hope you, you people would have get something, related to nanoscale and nanotechnology field. Thank you, sir.
Yes,
Anybody is having any query?
please check the chat box, ma'am, if you could find any. Okay. Participants, do you have any queries? If you have any queries, you can post them in the chat box available on the right side of your screen.
Screen is not visible or something. Her voice.
No, that's okay. That is okay. That is very far, ma'am. That's already done.
Yes, yes.
Okay. I have one.
Having...
I have a query,
yes,
ma'am.
Yes,
normally, I'm Krishna Prasad, ma'am, Associate Professor, EC Department, VVIT, ma'am.
Yes, sir. Good afternoon, sir.
Good afternoon, madam. Ma'am, normally all these VLSI design tools are very expensive, and
yes,
universities, institutions, and all other people cannot afford them, ma'am.
Sure,
and
yes.
we have, with the profile I have seen from NIT Patna Department of ECE, it is very strong in VLSI domain, ma'am.
These days, it is getting strong. Actually, we are having Xilinx, so we can get, but we are having Cadence, we are having Mentor Graphics, Synopsys, we are having. These days, we are having Cogenda also, and Silvaco, Atlas Silvaco is also in the purchase process. So yes, we can say like we are having enough tool,
enough structure, enough infrastructure available.
Yes,
in that way, can do we get any kind of help from your department, ma'am, for the participants who are willing to do some kind of research work in this domain?
Why not? See, this is a COVID time, so physically we can. You people cannot come, but yes, if I'll speak. So it can be like online licenses are also available. So with that particular thing, you can do work at your home also. Like online license, that means we can provide license to you, and you people can work. So this, some process will be there, but it is these days it is feasible. It can be done. Yes.
Okay, thank you,
ma'am. So you people can access that license, but with the help of concerned faculty and concerned person.
Okay, ma'am. So most of the participants are actually from faculty domain only, ma'am. So this might be useful to them, ma'am.
Sure. And most of the people, maybe they are doing PhD or post PhD also. For the profile enhancement, they have to work on these things.
Yes, ma'am. Any queries, participants? Okay, ma'am. So thank you very much, ma'am, for your wonderful technical session on nano-electronics for next generation mixed signal design. It is really very informational, ma'am. The topics related to mixed signal design challenges, nanostructures, and design and applications related to nanostructures, and knowledge from your research work. That was a wonderful. That was some very good work, ma'am. We could able to visualize it from your publications. So on behalf of the Department of ECE, Management of VVIT, I sincerely thank you, ma'am, for your encouraging and knowledge sharing, and we really looking forward for your next session also, ma'am.
Okay, thank you so much for inviting me, and thank you so much. Hopefully, whatever I have delivered to you, it will be helpful for you people in the future. And I'll be always be available whenever you people need me, or in any like in the field of research or any kind of things. So let me know if I'll be helpful to you people.
Yes, ma'am.
Thank you so much for inviting.
Yes. Can you share the slides to participants, ma'am? Is it possible?
So here only in the chat box, that attachment is there. There only I can attach, or what?
I will do one thing, ma'am. You can just forward it to the mail ID of our coordinator, ma'am, so that from there, yes, ma'am, we can forward. Sir, 1 second, ma'am. Murthy sir has got a question, ma'am. Sir, you can talk, sir.
Yes, please.
Murthy sir, please unmute your mic, sir. Murthy sir, please unmute your mic, sir. Sir.
Sorry.
Hello, sir.
Hello.
Sir.
My voice is.
Sir, your voice is not visible, audible, sir. Hello, Murthy, sir.
Sorry.
Sir, my voice.
Yes, sir. Yes, sir. I'm hearing your voice. Hello.
Your voice is now it is audible, sir. You can go ahead, sir.
Thank you. Information and not only basic information for nanotechnology, we give such a wonderful information, and meanwhile thankful to our VVIT management. We give we had to arrange the session. I thank you, madam. Hello.
It's visible. It's audible, sir. Audible, sir.
Madam, already sir is asking if it is possible to share our slides for participant mail IDs, madam.
Sir, actually, sir, the madam will be forwarding the mail complete presentation to our site, sir. From there, we will forward to sir, because it will be difficult for ma'am to gather all those mail IDs and all. Since they are available with us, we can easily forward them to you, sir.
Okay, sir. Madam, thank you for your wonderful information. Thank you, madam.
Thank you so much, sir.
Okay, thank you, madam.
Thank you very much, madam. And
okay.
Thank you, madam. Thank you very much.
Thank you everyone.
Participants, we have a break up to 1:45. At 1:45, we'll have a second session starts, and please be there. Please be ready by 1:45 p.m. We'll have a session starts at 2 o'clock. You have, okay. I think you have links also shared to you through WhatsApp and other means. So be ready. Thank you one and all for your wonderful participation. I once again sincerely thank Pushpa Giri ma'am for her wonderful session.
Thank you so much, sir.
Yes, ma'am. Thank you, ma'am.
Thank you, sir. Thank you very much.
Thank you, sir. Ravi Kumar.
Sir. Shall I leave, sir?
Yes, ma'am. Yes, ma'am. Thank you very much, ma'am. Thank you, ma'am.
Thank you, sir.
Yes, ma'am. Ravi.
Sir, what about participants?
Sir, participants you can leave and you can Ravi participants వెళ్ళొచ్చు కదా?
Leave అవ్వచ్చు సార్.
Okay. Next మళ్ళీ 1:45 కి జాయిన్ అవ్వండి సార్ participants అందరూ. Have your lunch and be back.
Okay, sir. Okay. Thank you, sir.
Thank you అండి. Thank you. Ravi